Okay, welcome back to Unit 2 Dynamics for AP Physics 1. In this video, we're going to focus on the spring force. And remember, we're continuing our journey down talking about applications of Newton's laws. So, spring force. What happens is springs are useful because they're going to exert a force when they're stretched, right, or compressed. So, stretch means you pull it apart. Compressed means that you bring it down together. So the force acts to restore the spring to its natural state, right? So the natural state means to be unstretched, uncompressed, right? Not stretched, not compressed, because that's what, so the force, the spring force that we talk about, that's what it wants to do. It wants to bring everything back to that natural state. So the amount of force, or excuse me, the amount that the spring is going to be stretched varies with the force applied to it. So the greater the weight or the greater the force, right? This could also be the word force. So the greater the force applied to a spring scale, the more the spring is stretched. So the spring scale is a special measuring tool that uses the spring and it's stretched. Okay. And as it's stretched, it reads how much weight is on it. That's how, if you go to a grocery store, that's how the produce scales work. Now, the force exerted by this ideal spring is proportional to the distance of it stretched or compressed. This is what we call Hooke's law, okay? And it's a proportional. So we say F sub SP is negative Kx. So this K is known as the spring or force constant. And basically what that tells you is how stretchy the spring is, okay? If K is small, very stretchy, right? So think slinky. If K is large, not very stretchy, right? Think garage door spring, right? So slinky, garage door spring. This X is what we call elongation. And this is how far it is stretched or compressed. Okay. Now, this is a negative sign because remember, this is a restoring force. So it's always going to bring it's always going to be pointed towards the natural position. Okay. And so here's just a quick little diagram. I may have written over top of some of it. So you can see we have a spring that is stretched, not stretched, then we pull it. Okay. And then talk about the force required to move the spring is F equals Kx. Okay. But remember that this spring, that the force also wants to restore it back to its natural state. So let's look at an example. So you got a spring with a spring constant of 21 newtons per meter. It's stretched 3.4 centimeters. What force is required to cause this amount to stretch? And how far will the spring be stretched if we double the force? So one thing I want to point out is right here, the springs don't stretch meters. They stretch millimeters or centimeters. So you have to be careful, right? Because note that this here is our K value, right? It's in units of meters. That needs also to be in units of meters, or you can put the K value in centimeters, okay? So what we're going to do is we're going to say F equals Kx, right? We're going to use our spring force, so F sub SP, and we're going to set that equal to 21, right? Because that's our K value. Now we got to convert our centimeters to meters, so 1, 2, right? So then we 0.034 meters. And that tells us that our force that we're applying to cause this stretching to happen is 0.714 newtons. Okay, so This, remember, is in newtons per meter. So when you multiply, you would cancel out the meters. That's why they need to be in the same unit. Okay, now, so that's part A. Part B talks about now if we double this force, okay, what happens or how far is it stretched? So there's a video called for our that we call the factors of change. So let's try that method here. So the factors of change telling me I'm going to plug in ones that remain constant. So in this equation, the force constant will remain, the spring constant will remain constant. Okay, and then we're going to plug in the factor for which, right, the factor of change for one of our other variables. So that's going to be, we're going to double the force. Okay, and so what does that mean? Our x is going to be double the distance, right? So our factor of change for x is now 2, because what we do is we solve for our unknown factor. Okay, so what does that mean? The distance that we're going to move it will be 6.8 centimeters because our original, right, was 3.4 centimeters. So I'm going to double it. The other thing that you can do is double that force. So it's what, 1.428, right, equals 21 times x. And then you solve this for x at 1.428 divided by 21. And surely there it is, 0.068 meters, right? Which when we converts to centimeters. So there's two methods, right, to solve this problem. This is called factors of change. Okay, and then you have your traditional algebraic solving of it. So in the next video, we're going to look at tension, right? So now we're going to look at what happens when strings and cables and so forth get